Well, good morning, just about. My name is Helena, I'm an architect in private practice here in Galway, and I'm giving you an overview of a study I did a couple of years ago in relation to just looking at the typical energy upgrades and the impact that temperature might have to the state incentivised typical upgrades present. I suppose we're all familiar with the context and why we all need to do this, and we're familiar with the nature of the type of works under the typical, at the time, the Better Energy Home Scheme in terms of our cavities and our attic insulation. And I suppose we're familiar why they're needed. But I suppose, having looked at some other research and other studies in terms of the results or how these perform in practice, I was kind of questioning, I want to explore basically, are we achieving the net energy and CO2 reductions from these typical upgrade projects? So I suppose various studies, a lot of them from the UK, I suppose would indicate that we have, we're not always achieving the predicted. I'm focusing mostly on CO2, so apologies if you're more used to kilowatt hours and everything at the end is in kilograms of CO2 as well. But that the CO2 or the energy reductions can often be much lower than predicted, with figures varying at some instances in really old houses to no savings, to maybe 40%, or perhaps the Energy Saving Trust suggesting reduction factor of about 50%. For retrofit works, that's typical cavity type works. There are many variables affecting these CO2 reduction, the CO2 reductions achieved, the actual insulation solutions used and the workmanship, the embodied energy or the embodied carbon, the materials used, the temperature conditions in the existing house pre-works, and the tenure, the occupant profile, the likelihood of temperature take back. So I was awarded a small bursary a couple of years ago under the RIAI 2010 research project to basically get a chance to look into this. And to get the project moving, I was supported a little bit by SEAI and by the department just in terms of linking me up with a study group. The project involved the monitoring of houses before and after state incentivized insulation works to basically quantify internal temperatures during both periods. This data was used to generate DEAP models to assess the impact of these temperatures on the predicted CO2 reductions post-work and any implications of that. So, Clwyd Housing have a housing development in Drumlish and Longford of 8 houses, 2 and 3 bedroom bungalows, and fairly simple forms, fairly standard houses built in 2001. And at the time they were undertaking works, these houses, the houses themselves they're installed a few standing stoves as the main source of heating, and usually mostly heat there with some coal as the fuel types in use. So the insulation measures, the insulation measures were typical of the grant-aided works. We had the pump beak in the cavities and high levels of attic insulation at ceiling level, achieving 0.12 watts per meter squared Kelvin. So they were well in excess of current backstops for existing houses. My technology wasn't very flash, but these are nice enough things to play with in terms of data loggers recording then the temperature and the humidity in levels in the house. So I didn't have a huge amount of notice as to when we were going to do the work. So I had to rush down and I got them in. I only got 4 days of data before they were installed, and then I could run it obviously a much longer period post-works in terms of data collection. So the loggers were located in the main living space in each house and then in the main bedroom. This was to allow me basically to calculate whole house temperatures or have a variation. It would be great to have had more, but I was kind of somewhat limited in monitoring resource. So I came out to each house, a living bedroom, and then I tried external data logging, did not work out for me, and I met a base that was quite a close weather station to use data from. So this allowed me to calculate for the houses the typical, the whole house temperature before and after the works. Basically, all the temperatures went up, which I suppose isn't that surprising for the houses. But so I needed to try and assess, well, why did it go up? We need to look at the external factors first. So we used the weather data, basically we used temperature, humidity, and looked at the solar radiation to see if they might have contributed, and to basically a trend and regression analysis of those. Basically, there was no really strong correlation to link the two. No correlation between internal and external for the post-works, and a very, very slight pre-works. So it was deemed maybe not to be a really significant contributor. May have a little bit not significant relative to the temperatures that we observed and the increases. So the temperatures got hotter, and they were already hot, though, warm in those houses. Those houses were 20 degrees before we did any work, before the works were done, and some of the houses went up, the guts of a degree or over half a degree. So, sorry, I'm jumping around. So, so I suppose the extent then of that take back, it's maybe a bit more difficult to determine why. Some of it would be the building itself. It's obviously it's increased its thermal resistance is much improved, so it's going to retain heat better. So there's an element of that which is quite difficult, but some studies would suggest that that might be maybe 50% or encounter about that of the temperature take back. And then there's obviously then the other portion of the nature of the occupancies, basically and how the occupant interacted or dealt with the changes and modified their behaviour at all. Another interesting as part of it, maybe the routine nature of lighting something like a stove as distinct from thermostatically controlled, and the impact that might have in terms of that form of heating might have on terms of the delivered or the achieved CO2 reductions post retrofit. So I then had the exciting bit of bringing it into DEAP, and I suppose there's two aspects of this. So first of all, I looked at the 3-bedroomed house 8, and I calculated the embodied energy with reference to Hammond and Jones' inventory of carbon and energy at the time, because I could not get manufacturer's data here, and we don't have an Irish equivalent at the moment. And the DEAP prediction was demonstrating that the dashed blue line is what DEAP would have predicted as the predicted savings. When I adjusted the internal temperature within DEAP for the house through Paul Martin and nZEB facilitated an unprotected copy for me, that showed that basically we had dropped the orange line being with even a modest take back of 0.3 of a degree of increased temperature, that we've lost out of 28% of the savings we thought we were going to get. Again, similarly with house 4, again the embodied energy is very, very low. The materials aren't having a major impact. The DEAP projection all looks great. And the house was a little bit higher, so that in a sense suggests there should have been maybe more savings pre-works. But when we looked at the 0.9 degree take back increase in temperature, that really hammered this particular house in terms of their projected energy and CO2 reductions. So that brought down, they'd lost like 78% of the potential CO2 and energy savings as a result. So I suppose what that kind of meant, or what that suggested, the pre-works temperatures indicate they're all in around 20 degrees, which should have suggested that it should have been very low temperature take back in those houses. So 20 degrees would be kind of, I suppose, as a whole house temperature, seemed to be pretty much the ideal of where you would be at. And maybe 21, you're actually up to saturation point, you're definitely nearly past the upper limit. So on that basis, it should have been a very low temperature take back predicted as a result of the work. So we should have been maximising and coming away with 100% or close to maybe 80, 90, 100, or perhaps 15. It varies mostly, again, UK studies would suggest that kind of range of 80 to 90% perhaps. You should deliver the higher the temperature, maybe that's a lower reduction for comfort. So the DEAP model that I undertook, based on a short period of monitoring, which is a limitation to it, suggests that it could be much more significant, or at least for the initial period after work, perhaps until people adapt their behaviour. It may not be ongoing, there's no questions, but I suppose there is a worry that in any event we're losing out on any of it, or anything like that percentage, even for a short period. So the 22 to 20, we've lost out on a really significant, nearly 3/4 of the potential savings. So then that in itself, that take back's higher than expected, and I suppose worrying if it were to continue over a period, or if it was linked to particular forms of heating in certain houses, or whatever might cause it. So if you looked at then, what does that mean for the embodied energy? So for the typical the pump cavity and glass mineral one in the attic space, we're looking at very low embodied energy. So we're paying back there in about 2.3. The carbon payback is about 2.3 years, even with take back, quite a high degree of take back. So that's not a worry in that sense. But as we start to look at slightly more energy intensive materials in terms of maybe a dry lining board to the equivalent performance as our pumped cavity, certainly we're looking at maybe a 10-year payback. So suddenly that take back starts to have implications for other things that wouldn't normally have, that you wouldn't really need to worry about with relatively low embodied energy measures. So what happens then if we go deeper retrofit? So that's a foot. We didn't go a foot in the model, but we went more like current backstops for upgrade work. And okay, the embodied energy has increased significantly, but at least we are achieving net, our payback has increased, but the quantity and the extent of CO2 savings over the lifetime of the building is much increased also. So maybe increased or deeper retrofit might be a way of buffering or reducing the risk of the impact of take back in particular risk that might be an issue. So I suppose to kind of sorry, a second. So I suppose to kind of summarise where we got to on it. The principle of take back concurs with other research. You would expect some, but not anything like the level that was indicated in, again, the short survey. Now there are limitations with it, not even hardly call it a sample, but anyway, very, very small sample size and a limited monitoring period. Again, difficulties with gathering fuel data, and then the lack of the opportunity to have a whole house or monitor throughout the whole house to ensure that your average temperatures are actually accurate in your assumptions. Again, limitations, the use of deep versus dynamic simulation modeling, perhaps much better feel for what element is occupant in terms of the take back in temperature, and what element of it is relating to the building, and it's just due to its increased thermal performance. Again, then I suppose there's an unknown in relation to the role of the occupant, and maybe even better information or how behavioural things maybe can be dealt with, and how and might they modify that initial behaviour, that behaviour over those 3 or 4 weeks after? May they have modified that over time and actually adapted a little and not and reduced some of that temperature take back? And particularly interested, I suppose, is the solid fuel aspect to it, the difficulty with controlling of that, the routine nature of that. I have clients myself, a client in a passive house who is addicted to the fire, so rather, I don't know, see how it gets on this winter with it, or this autumn perhaps, but there's that routine element of feeling that you have to have fire, so, or for people in this, in that, using that form of heating. And again, there's really a complete lack at that time, and there may be other studies since, that finding any kind of useful data or studies in relation to upgrades to houses with the more conventional stove or syringe system that we're familiar with here, particularly in the Midlands. So to summarise, the pre and post works internal temperatures were higher than a lot of studies would suggest, and that would be assumed in DEAP. So the higher level of take back observed, again in the limited monitoring period, kind of brings in some risks or some issues with relying too heavily on DEAP, a risk of overestimation and of implications for payback of the measures or the savings of people or the elimination of food poverty or whatever the aim of that retrofit measure was. The embodied energy of the materials becomes much more significant increased take back. So we have to deal with all these harder to treat, these colder houses. They're the houses that probably haven't really been tackled that much yet, and they are the ones that there's a much higher risk of the temperature take back. So that's maybe if policies need to adapt for grants related to those houses, that embodied energy becomes much more of an issue. And then the requirement for deeper, perhaps another kind of a way of maybe reducing the risk of coming out with no net savings, or to ensure that we do get net savings, might be a requirement for deeper retrofit for those harder to, those particularly cold houses where there is that increased risk of significant take back. There's no more studies in this area, but and a few things to think about.